may somehow suggest may indirectly suggest the effect of some doping abuse. One example, there are different modules within this athlete biological passport. One of these is the haematological one, which characterizes and defines the blood biomarkers. So in this case, for example, athletes may use some substances to enhance oxygen transport or delivery, for example, EPO. And the two primary biomarkers within this module are the hemoglobin and the OFF score. So I would like to highlight the two because these are the two we are going to work on for defining our multivariate framework. And these are the two based on which the World Anti-Doping Agency implements the analytical framework. So, for example, as you can see here, we have the individual profile of the two biomarkers. And as you can see that for each of those, you have some individual ranges. And as new samples are observed, these individual ranges may change. And when a value falls outside this individual range, it may suggest a doping violations. And those observing such values will prompt further investigations. And currently, the way these ranges are built is based on a methodology, a Bayesian analytical framework, which is called the adaptive. And all the national agencies, they will be given by the results from the platform which implements this methodology automatically. So no one will have to carry out this analysis by hand. This is going to be given by the platform itself. So let me summarize a little bit how this adaptive framework works. This is the state of the art, so it's important to outline it a bit because we build on it. So we maintain the actual framework. So let me provide a bit of notation. I'm sorry, this is a bit heavy, but it's somehow mandatory. So let's consider some outcome related to a biomarker L. Here we consider two biomarkers, hemoglobin and the OFF score. Let me mention that the OFF score is a derived quantity from the hemoglobin. It's a combination of this and hematocrit. And let's denote with YLIJ as the outcome of the marker L measured on the athlete E on occasion J. So for each athlete E, for E going from 1 to N, let's assume that we have TI measurements so that for each athlete, a different number of measurements can be recorded. Let's also consider the whole history of readings for athlete E as Y undersigned. And let's assume that this Y is defined based on these two biomarkers, and the bold notation denotes both of them. So we are in the R2 space. Sometimes we also characterize these biomarkers based on some explanatory variables, age, gender, and so on, all the variables that are expected to somehow inform values that we can see for this. And let's now consider a new test sample, which is basically the test, the variable for which we want to build a prediction set, a prediction intervals, a reference range, such as the one just seen here. And according to which, once we will observe the value of the outcome at time ti plus 1, if it will fall within the reference ranges, then everything is fine. Otherwise, further investigation is suggested. So the goal is to decide whether this test sample, once it is observed, conforms to the historical readings, or whether it constitutes an atypical finding, conditional often on the set of covariates. So the general problem is basically to provide a probabilistic framework to estimate a conditional probability distribution in a similar form to this one. So basically the probability that yi plus 1 conditional on all the history of the readings. So on the individual profile, this is collected within the athlete biological passport, and its individual characteristic. So basically this probability here. So in conjunction with a decision rule, this probability here can be used, this probability distribution can be used to define these individual reference regions for the new test. And as mentioned before, if the observation will fall within the reference region, then the sample is going to be considered normal. Otherwise, it will be considered atypical. And the main characteristic of the current methodology, the adaptive one, is that this probability here is defined based on a Bayesian paradigm, and it is nothing else than the prior or the posterior predictive distribution. It is the prior, of course, when we have not observed any previous reading for the same individual eye. And the model currently implemented, of course, reflects the biomarker which is under consideration. For example, within the haematological model, where we have hemoglobin and the OFF score, this is the model proposed in 2008 by Sottas and colleagues. And this is a hierarchical model where basically each observation, so the outcome for each of the biomarker follows a normal distribution, and the assumption is that conditional on the parameters, they are independent within time and between. So within individuals at different times and between different individuals. And then some prior distributions assumed for the unknown parameters. And as you can see here, the equation number one defines a specific, the variations occurring within the same individual, while equation number 2, so with equation number 2, I refer to both of them, define basically some population-based characteristics. So it combines together the inter-individual and the intra-individual variation that can occur for an athlete. And based on this model here, a predictive distribution is derived as given here, where basically this represents the distribution that we assume, which in this case is a normal distribution. This is for the new test, and this is multiplied by the posterior distribution of the unknown parameters, so mu I and sigma. Mu I and sigma, of course, are the mean and the standard deviation of the normal distribution characterizing the outcomes related to individual I. And mu I is specific to that individual. So in this case, if we are referring to a posterior distribution, then the posterior distribution reflects for the prior distribution, the inter-individual variation, but at the same time, since it also accounts for the individual trajectory of I, it also takes into account and calibrates the reference ranges according to the intra-individual variation, so to the specific characteristic of each individual. So that's why when you look at these reference ranges, this will change over time, will change according to the values that we observe for the same individual over time. So this reflects the name of the methodology, which is called adaptive, because adaptive are the reference ranges. Now, what is the issue with this framework? Well, the issue is that it looks at each individual trajectory of the athlete biological passport, at each individual biomarker univariately. So it doesn't account for the interrelation between different biomarkers, and it builds reference ranges simultaneously. So this may cause several issues and also reflects an underlying reality, which is not the one that is seen in this biomarker. So the first type of issues are the statistical issues, because we are building some simultaneous univariate, we are doing some simultaneous univariate analysis, and this may, when one constructs multiple reference ranges and the same level alpha, for example, the same miscoverage or significance level is considered, this may lead to inflated undercoverage or inflated type 1 errors. So this is point number B. But at the same time, since predictive distribution are derived separately, they do not account at all for any dependent structure between the different biomarkers. And I have decided to display this, this plot here, which basically represents say the expected distribution of hemoglobin and the off score. So as you can see in this plot, the two have a relationship. The two are highly correlated, and this relationship is not even symmetric, for example, as the one that you will expect in a multivariate normal distribution, and it also has some tail dependency. So it shows some complex dependence structure. In addition of showing some distributions, which, for example, in this case, are far away from the simple normal distribution. So perhaps it will be more similar to some mixture of normal distributions. So these are basically some of the main statistical limitations. And there may also reflect some biological issues. For example, when you model biomarker variables, which are, and you model them independently, you actually assume that they provide some orthogonal information. But this may not be true, either because they are derived quantities. For example, the off score is a derived quantity of the first two biomarkers here, hemoglobin and hematocrit, and intrinsically it will have some relationship with the two. And the second aspect is that whenever you tackle a problem such as the doping abuse, even if in a control population, they may not have some, they may provide some orthogonal information, we don't know whether simultaneous alteration of these biomarkers due to, for example, the presence of prohibited substances may actually induce and lead to some different or some specific dependency between the two. So this is the plot, and here, for example, this is a picture taken from SOTAS 2008, and here you can see how these biomarkers change when some doping substance is taken and how they change together. So they all will change simultaneously. And when trying to understand different dependency structure, actually in the statistical and probability literature, we have these models, Copula models, which are intended to capture, to reflect different dependency structure between variables. So for example, here you can see structures which show a symmetric dependency, the normal one, and the Frank copula, for example, similar to T copula, where you also have some dependency on the tail, and also structures where you will see asymmetric dependency. So for example, if you look into the Clayton copula, you will see much more dependency on the left tail compared to the right one. And if you look again to the Clayton copula, you will also see some similarity with this plot here. It's not exactly the same because here is more reflecting more a rotated copula, a survival copula rather than the standard one. So again, to stress the importance of copula compared, for example, to to other multivariate model, because the issue is not only to build a multivariate framework, but also to build a multivariate framework which may be able to capture complex dependency structure, is you may look at the following picture. So here we show some data. Here we have hemoglobin and hematocrit. And if we look at this dependency structure, and if we plot on top of it the contour of a normal distribution, what we can see is that we have some points falling outside here, which indicates some tail dependency, which is not captured by the normal copula. So it's not captured by the normal multivariate distribution, as the first is shown to be the copula of the second. And it also, the real data shows some asymmetry, which is again not captured by the normal copula, which is symmetric by definition. So let me introduce some formality of what is a copula when it was introduced. So it has very old origins. And the main result, a representation theorem due to Sklar in 1959, states that if we have a random vector independently on the number of dimensions, here I'm taking 2 dimensions for simplicity, and also because it's the setting we are working on, and we have its CDF represented by this Fy, then Sklar showed that there always exists a function, which we call C, which is our copula. In this case, it's a 2-dimensional function, but in general, if you have a d-dimensional vector, it is a d-dimensional function, which goes then from the space 0, 1 to the power of the dimension to 0, 1. And this function is such that it can represent the cumulative density function of our random vector y through this relationship here. So through the copula in with arguments, the marginal CDFs in the 2 specific points, y1 and y2, for each of the points that we can take in the R2 space. And if we are dealing with the continuous variables, so a variable for which a density function exists, then this representation here is unique. Not only it always exists, and has the following density representation. So we can basically represent the multivariate density of our random vector y as a product between the marginal univariate densities and the copula density with arguments, the marginals, CDFs, in the points of interest. So we want to use this setting here, this probabilistic setting, to build a multivariate framework and to couple it with a more sophisticated model on the lines of the one introduced by Sotas in 2008. So basically, what is our goal? So we want to maintain this framework and we want to adapt it so that it can be accepted by WADA's practices. By doing what? First, by accounting for multiple biomarkers jointly. So accounting for them jointly means that we also want to model the dependent structure, and we do this with copula models. Then we also want to factor in individual characteristics with more emphasis. So we extend the model to a random effect model. And we consider different parametric families. So we propose a framework which is very, very general. and it goes beyond the Gaussian marginals, but it is still parametric. The second characteristic of the proposed framework is that we move from univariate interval, univariate reference intervals to multivariate predictive regions. And this is going to be done with the use of conformal prediction theory, which comes with some coverage guarantees. So let me start with part number 8, sorry. So in part number 8, we focus on the model. So what do we propose for our marginal distribution? As mentioned before, we propose a random intercept linear mixed model where the outcome of biomarker L for individual E at measurement J is represented as a combination of, as a function of some decovariates with some specific unknown population level parameters and some individual level effects, plus the random noise. For example, we propose it in a very, very general way where everyone can choose a generic parametric family, which depends on some parameters, say parameter mu, which is the parameter related to the mean, and some other set of parameters, eta, which can be related, for example, to the scale of the distribution. And each of the parameters within this distribution are then modeled themselves following the same similar hierarchical structure within the same Bayesian framework. So we propose normal distribution for the population level parameters and the individual level parameters, and some, for example, here, this is the variance of the individual level effects. For this, we propose a half T distribution, which is basically defined on the positive values, and some suitable prior over the specific family parameters eta. This, of course, will depend on the family that you take into account. So if you account for a normal distribution, this can be the standard deviation or the variance. And to complete this model, since this only refers to the marginals, we couple the two marginals with a Copula model. Again, we are considering only parametric family. Here, I'm presenting only parametric, only results related to the parametric model. And we basically couple, we proposed a model which reflects the dependency structure, which is given as follows in equation number 5, where basically Uij, where each single Uijl, so Uij HGB and Uij off score, hemoglobin and off score, represents a pseudo observation, where the pseudo observation is nothing else than the CDF evaluated in the specific point Yijl. So this is, of course, a bivariate vector in this case. It depends on a parameter, which we denote by theta cop, and we assume that it can follow a generic family denoted by C, and we will later make some assumption on this generic family because it will reflect the data that we are taking into account. And similarly to the hierarchical framework for the marginals, we use a Bayesian framework and we consider some prior distribution for the unknown parameter of the Copula model. I will use later on in the empirical results the notation MBT cop to refer to this proposed model, and uni to refer to the univariate framework discussed previously. Taking into account our interest, so taking into account the interest in this probability distribution here, so the posterior predictive distribution or the prior predictive distribution, if we don't have any data collected on individual I, then by using a Copula representation, we basically can derive this posterior distribution this predictive distribution, multivariately, by basically coupling the marginals, each individual marginal, with their dependency structure given by the copula. Notation is a bit heavy because it reflects all the longitudinal setting, all the different individuals, and all the different parameters that we have here. But what's important to notice is that basically we split the full distribution into two univariate distribution given by the distribution of each single biomarker and their dependency structure. Of course, since this is a predictive distribution, we also have to account on the distribution on the parameters, since we are in a Bayesian setting, and this distribution is since we don't know the relationship between the parameters and they may have a relationship, this is a joint distribution. And the problem now is how to estimate this joint posterior distribution. Again, I want to notice that if no observation has been observed for individual I, so if we are at tie I equal to 0, so our new test is basically yi1, then this posterior predictive distribution boils down to the prior predictive distribution itself. And the reference region is determined based on the inter-individual variability, so all the population level variability. But it is very important to also accurately estimate the prior, because otherwise reference ranges are not going to be reliable. And it is as important as the estimation of the posterior distribution. So that's why in this framework, we will follow the same procedure for estimating both the prior and the posterior. So as mentioned before, the problem is now how do we estimate this, say, complex distribution? It is a distribution of the posterior parameters, and the parameters are both the parameters of the marginals and the parameter of the copula. So in the typical approach followed in the literature for estimating such joint distributions is especially because often the problem is quite complex, because models are quite complex, copula models are quite complex, is called inference functions for margins. And this is a frequentist approach based on two stages, where at the first stage, one estimates the parameters of the univariate marginal distributions, and at the second stage, one estimates the parameters of the copula, keeping fixed the parameters from the stage one. So this is a procedure which has good theoretical guarantees. For example, it leads to consistent estimates, but it has been criticized over the years because it lacks a proper uncertainty quantification, and it doesn't come with known distribution on the estimators. So a lack of proper uncertainty quantification is due in this case, and we have decided to adopt a Bayesian approach, so to extend this inference function for margins from a frequentist to a Bayesian approach. So basically, the two stages are the same. In stage one, or step one, we estimate the parameters of the marginals following a Bayesian approach. So we basically, for example, we could get some posterior draws from the univariate distribution, approximate one of the marginals. Then we do the same for the other marginals. And then we use the samples from the posterior samples to get pseudo data U. So basically to evaluate the value of the CTF in YI given the draws from the posteriors. And in the second stage, we keep the draws fixed, and for each fixed value, we get M1 posterior draws from the copula model. So basically here, we keep the elements from the first stage fixed, and for each of those, we estimate another set of N or we get another set of M prime posterior draws from the Copula model. And at the end of the day, we are able to return some posterior draws from the joint set of the parameters. Let's go now in part number 2. So now we have these parameters. We have some draws from the parameters. We can have some estimate on the posterior distribution. And by having the estimates on the posterior distribution, we are also able to get some estimates from the posterior predictive draws. So we are able to get a range of values which we expect to see for our new test. But how do we build a reliable prediction region? And more specifically, how do we build a prediction region which may come with some guarantees? So what we want to do is we want to move from we need to move from the univariate context where we build reference intervals, such as the one that you see here, for example, for one of the 2 biomarkers, to a setting in which we build a univariate region, a simultaneous region for both of the 2 biomarkers. And this region will depend on the dependency structure. It will only be this kind of rounded region if you don't have any kind of dependency. So if your data are independent, but even if you do that, and if you use this kind of region, you are not ensured to have the guarantees that you want. For example, you are not ensured that you may cover 1 minus alpha% of your sample or 1 minus alpha% of your distribution. So we want to extend to go from the univariate set to the bivariate set, and we want to account for the dependency structure, and we want to guarantee that a specific coverage level is obtained. And how do we do that? Well, the conformal prediction theory actually comes into help for this task. And under some assumptions on the data, for example, in this case, the data can be our draws from the posterior predictive distribution, it ensures that the probability that a new test will fall within this region is going to be greater or equal than 1 minus alpha, where 1 minus alpha is our coverage level, the one that we want, and yit I plus 1 is the new test for which we want to build a prediction region. And R is the prediction region at the level alpha. And usually a very well-known type of region which is used in Bayesian inference are the so-called credible intervals or highest density regions, which were studied over the years quite a lot. And they all have very nice interpretation, but especially if the model is misspecified, they do not come with frequentist guarantees. So let's look now into how the conformal prediction theory and implementation actually process gives us some guarantees on the coverage. Well, perhaps I don't have too much time to go into details in this into this framework, but I leave you the reference, the main reference related to it, which is the one of Wolf. So in practice, how do we estimate our predictive region? So, well, we start with a bag of some data. The assumption on the data is that they should be exchangeable. So, for example, in our case, this data could be our predictive draws, posterior predictive draws, if they are, typically they are expected to be IAD. So if we have them, then we have the first ingredient to perform conformal prediction. Then we need some sort of conformity or non-conformity measure, which is basically a measure that measures how similar is one of the draws or one datum here to the bag itself, so to the other set of the data that we are given. So for example, as this measure, we use the posterior or prior predictive density. And what we build at the end of the day is a sort of highest predictive region. But by using the following procedure, we are ensured to have these guarantees. What is the procedure in a few words? The procedure gives us, allows us to derive a region, a conformal predictive region, given by all the points for which this R of y is greater or equal than alpha, where this R is basically defined as the ratio between the rank of the of this measure, okay, the observed measure, divided by m, which is the size of our bag. So this measure here, as mentioned before, is just a measure that measures the distance or the conformity between the bag excluding this sample, the sample that we are, for which we want to measure the conformity, and the sample itself. And it, being a rank, it has some characteristics, and its characteristic allows us that the region, which is defined in this way, with the rank greater or equal than alpha, gives us a region with some guarantees on the coverage. And when I said it has some characteristics, one of the characteristics that is given by this function here, by this value here, is that it represents a valid p-value. Indeed, it is a rank over all the different distances, all the different conformity distances. And in practice, to implement this algorithm, what you do is you assume that you have a grid, and on this grid, you compute this rank and you compute this value for all the values of the grid. So it may be computationally intensive. There exists other procedures which reduces this computational expense, but in this case we use it as it was not an issue for us. So we use a full conformal predictive framework. So let's now, working together on the extension A and B, let's now look into some results we got. So we basically, the first results relate to some simulation studies, and these simulation studies are entirely guided by some data on a real data set of control population. You can find this data in an R package as well called ABPS. And it contains a set of 12 hematological biomarkers measured on 3 different individuals. It is quite a small sample, so we decided to use some a kind of bootstrap approach to enlarge this sample. And following its distribution and underlying characteristic, we defined the following data generation process, where the 2 marginals follows one, the normal distribution, and the second one, a mixture of normals. So this also resembles the plot we have seen before. And for the Copula model, we used a survival Clayton. So this is the one setting that we have generated from this data generation setting, and the blue points represent the 2 data points on the real data. We decided to compare different strategies that differ in terms of the type of approach for the predictive inference, either univariate or multivariate, either well-specified or misspecified. So for example, we have considered a misspecification of the copula only, and the misspecification of the marginals also. So in this case, a fully Gaussian model, and the approach to estimating the predictive region, either a univariate one or a multivariate one. And I want you to notice that this is basically the approach proposed in SOTAS, And a kind of hybrid approach has later been proposed, actually very recently, by the team of Eleftheriou. So comparing these 6 different approaches, where this is the univariate approach, the one of Satas, what we can see is that when reference regions are built following a simultaneous univariate approach, this will lead to a kind of square or rectangular region, and this rectangular region will not represent the structure of the data quite well. The multivariate approach will represent the structure of the data in the sense that it will represent the dependency structure, and even in the case of misspecified models, for example, this, the bottom left plots, you will see that the region is much more accurate and takes into account this dependency structure. This is only an illustrative examples. Some more intensive simulation studies are reported in these tables. I'm not going to go through all of them. What I want to show you is first the miscoverage. So using a conformal prediction approach, we are guaranteed that the multivariate approaches always ensure a coverage guarantee of the specified level. And the other things I wanted to show is that in terms of all the performance measures, false positive rate, false negative rate, and other measures combining the two, the multivariate approach always outperforms the univariate one. And in particular, Copula-based approaches, even when these are misspecified, as in the case of Frank Copula, rather than the Clayton Copula, it results in better results. So time is running. Let me only spend a few minutes by showing you a real case of an athlete convicted for doping. So you can find this data in a report released by the Court of Arbitration for Sports, the Swiss one in 2012. And here you can see the individual profile of this athlete in terms of the 2 biomarkers, hemoglobin and the OFF score. And eventually this was convicted for doping. So as one will expect, perhaps all these measurements were related to some doping abuse. And when trying to identify this, which of these points, which of these measurements is an outlier or an anomalous value with the different approaches, what you can notice is that, so we have done this now with a more, with a different coverage level. This is the one typically used by WADA. It's a more conservative one. So what you can notice is that the univariate approach always includes, there is one point, so not all of them, but there is one point, the red point here, which based on the univariate approaches, so this is the one currently implemented, this point is always considered normal. So based on this point, this athlete will have not been flagged for further investigations. Of course, clinicians and experts in the field will have a better knowledge than the analytical framework. But since we also rely nowadays on analytical frameworks, and since we want them to support our decision-making, having a multivariate framework here actually will have given a better alarm for this individual, because in all of them, even in the misspecified cases, this point is flagged as anomalous. And it is flagged as anomalous in almost all of the cases. So this point, the red point is P11, and with the multivariate approaches, this point is never included in the highest predictive region derived by the conformal theory. And another thing given by the conformal theory is that for each point analyzed, it provides an empirical p-value, because the R function that we have seen before has the characteristic of a p-value. It has a uniform distribution. And if we look into the value assumed by that function for each of these different points, we can see that while P2, P8, and all the points which were never included in the highest density region, this p-value is always lower than this significance level alpha here. While for the others, it is higher. So it doesn't suggest the possibility of rejecting the fact that that point can be normal. So let me now conclude. What we have tried to do is we have tried to extend the current framework, remaining in the Bayesian framework, remaining in a hierarchical model, but trying to use and to understand what is the multivariate characteristic of multiple biomarkers. We have done so by using Copula, which are able to disentangle complex dependency structures. And we have done so by using conformal prediction theory with frequentist, which leads to frequentist coverage guarantees, even if we are in a patient setting. Of course, there are some future work, some ongoing and future work. For example, we are now trying to implement it on a real big data set provided by the National Agency of Doping, the Italian one. The other one is to include covariates, and this is going to be done with the data provided by NADO to account perhaps for multiple biomarkers, even if nowadays the haematological model only focuses on two, and also perhaps to compare our strategy to other anomaly detection techniques. So thank you for your attention. And I was hoping to end a little bit earlier to allow for more questions, but I mean, we are still in time for some questions. So I'm waiting for them. Thank you very much.
Excellent. Thank you, Nina. Yeah, you can see the customary applause icons.
And some references.
Yeah. So yeah, we do have a few minutes for questions. So if you have questions, if you'd like to raise your hand and I'll call on you. Let's have a look. I had a question to get the ball rolling. So this reminds me of things I've seen in medicine. I work in medicine, where they're looking for, you know, how these things with a nurse, maybe there's a number of deaths in hospital, like child deaths, and they want to know if that's an anomaly, so that or a GP, for example, and things like that. So how does that relate to those sort of detection algorithms? So I've seen them where they have sort of these sort of like funnel plots, and you know, it depends on the sample size for the variation.
Yeah. Yeah, I think the setting is not so different. I mean, I think they also work on defining some reference ranges, reference
Yeah.
regions. I'm not sure, but I suspect they still work using being in a univariate framework. So they look at different values, they look at different variables following a univariate approach, which is likely to miss some important, dependency structure. So, but yeah, I think the problem is quite similar. And this problem is quite common in many settings, like even, when you do some quality control.
Oh yeah, of course.
Biostats and outside biostats. So here we were completely motivated by this problem, but I think that this framework could well be applicable to other contexts outside the one we look into.
That makes sense. Thanks.
Thank you.
So are there any questions? There don't seem to be. Um, well, I might because I'm the chair. I can ask two questions. How does time come into this? Because the measurements are taken over time, but were you just using those as a bag of data?
Yeah, yeah, very good question. So in my case, yes, I use, so when applying, if you refer to the conformal prediction case, I used the samples from the bag as my grid. So by doing that, I did not run again and again all the different, like all, I did not evaluate all the different elements from my grid, from my bag on a new set of data defined by the grid. So it actually was not too computationally intensive. I will say that perhaps the most computationally intensive part here is all the posterior parameters approximation, because it involves a lot of MCMC parts, MCMC parts for the marginals, for the copula, but still, since you work on the marginals and then on the copula in the two-stage approach, it is less expensive as the one that will be required if you will have to work on all of them jointly.
Yeah, that sounds reasonable. Oh, we can finish with a last question from David.
Yes, I know what hemoglobin is, but what's OFS stand for?
Sorry?
I know what hemoglobin is, but the other drug.
Okay. So off score is a combination of hemoglobin and hematocrit. So it is a linear combination. So no one should expect it to be, independent from the hemoglobin one, since it is a direct linear combination of the first one. So I have a function somewhere summarizing the linear relationship, but in order to understand it, yeah, it's just a linear combination of the first one and another biomarker, which is hematocrit.
Oh, it seems funny that hemoglobin comes into both of them then.
Yes, it does.
Thank you.
So it does, and I think this is my intuition while looking on at the different plots and data. What happens is that the second one, being a derived quantity, is much more sensitive to any variation. So for example, if you look here at the concentration of hemoglobin, what you will notice is that, so at point number 8 and 9, you have a small increase in the hemoglobin, which translates in a great increase in the off score. So the off score looks like to be a more sensitive biomarker to variations from the normal level. So if one is somehow expected to have taken any doping substance, then the off score is going to reveal it more intensely.
So how much does having the hemoglobin separately add to the information you get?
I don't know, but this is something I should ask to the specialists from the World Anti-Doping Agency, because this is their practice. So I'm not able to answer this question. I guess they have more domain theory to answer it, but yeah, their practice is entirely based on these two markers.
Okay.
These main two markers. Analytically, these are the only two markers which prompt further investigation if a value falls outside the ranges.
Okay, thank you very much.
Thank you.
Okay, on that note, I think we're going to leave it there. So just to say thanks very much, Nina. I really enjoyed it. I'm sure everyone else did. And I'll be in touch by email afterwards. So thanks again.
Thank you very much, Nathan. Thank you,
Bye.
David, for the question, and thank you everyone for attending.
Great. Bye.
Bye.